Hello ladies and gentlemen, I am Dr. Claudia Albers, Planet X research and professional physicist, and today I'd like to bring to you another one of my articles. This one is entitled Stellar Core Evolution. Now in the previous article, article 183, entitled Stellar Cores Absorb Photons which carry gravitational energy, I explained how stellar cores absorb photons which are carriers of gravitational energy, which are thus their source of energy. In this article, I describe how stars evolve into stellar cores, why stellar cores are attracted to the Sun, and why they are able to hover inside the Sun's corona. Now in this image we see two stellar cores. We see a dark one here, and we see the connection that it's making to the Sun, and we see another stellar core. This one seems to be enveloped in plasma from the Sun's corona, so it seems to now be able to emit some light. And we see another one partially within the Sun's corona, and again the particle connections that it is making with the Sun. And these are gravitational. These are due to gravitational interaction between the stellar core and the Sun. Now, both the gravitational interaction and the interacting particles come out of light or photons as these split into their constituent particles when moving through an area of high enough electric field. It is all due to a balancing act between the gravitational and the electrostatic interactions that matter forms atoms in stars and galaxies. So the electrostatic interaction causes protons and electrons to attract. It causes two protons to repel and two electrons to repel, and the strength of the interaction is the same in all cases. It's also described by a property called charge that protons and electrons have, and the proton is assigned a charge of plus E and the electron is assigned a charge of minus E. Now in the gravitational interaction, the proton is repelled by the electron. Two protons attract and two electrons attract. But the interaction between electrons is extremely weak, and the interaction between protons is extremely strong, especially if they're very close to each other. And the interaction between protons and electrons is of it's between these two, I suppose, and this is because it's partially based on the mass of the particle, and that is the property of matter that describes gravitational interaction. Because the proton is much more massive than the electron, the interaction between two protons is much stronger than the interaction between a proton and an electron. And the other part of the interaction has actually to do with the photon that the proton and the electron come out of, and thus the interaction can have different strengths depending on the energy of that photon. Now, since a star uses its gravitational potential energy to produce light and matter, it will have less and less gravitational potential energy as it ages. As the gravitational potential energy of a star drops, so will the electric potential between the core and the outer negative layer. And so eventually the star will not be able to have electric discharges, and thus will not be able to emit light and have a solar wind or have CMEs. This is most likely why the system of stellar cores that have invaded the solar system are not seen when they enter the solar system. In other words, they're not emitting light. As the star loses gravitational potential energy, the attraction between protons in its interior would also decrease, resulting in the star expanding in size. In addition, the star would exert a lesser attractive force on outside objects, and thus its effective mass would decrease. The star will therefore seem to have less mass for the amount of matter that it consists of. Stars are also likely to lose electrons from their outer negative layer, as these would be likely to gain enough gravitational energy through absorbing photons and would thus be able to leave the outer negative layer or corona of the star. They would then most likely form another outer layer beyond the star's capacitor rings at the outer edge of the star system. Thus, a stellar core as an old star would most likely be deficient in electrons and thus be a superion. As a superion, the old star would be electrostatically attracted to the Sun because it has an outer layer of electrons. That is, the Sun has an outer layer of electrons. It would also not draw a current inside the solar capacitor like comets do, which is likely why stellar cores do not seem to develop comet tails. They only draw short proton tails once they get to the Sun, and this is due to the gravitational attraction that exerts on matter within the Sun. And this only occurs once they have interacted with the Sun electrically. Now, here we see illustrated what happens, what causes stellar cores to be attracted to the Sun, and it's basically the fact that they are positively charged, and they most likely have a neutral outer layer instead of having an outside layer which is negatively charged, which the Sun has. So, because it's positive, it will be electrostatically attracted to the Sun's outer layer of negative electrons. So here's the electrostatic attraction represented. There will be a gravitational attraction, but it will be very small because the star has a very small effective mass. So the main attraction is electrostatic, and once it touches the Sun's corona, it will gain a layer of electrons and thus equalize the charge between the interior and the outside. Now, all this occurs because, first of all, photons split into protons and electrons when they move through a region of high electric field, and this is what is represented here. Then once the protons and the electrons come out of the photon, or thus are created, we can have the formation of neutral atoms, and a neutral atom has protons in the nucleus on the inside, and it has electrons orbiting the nucleus. So the simplest atom is the hydrogen atom. It only has one proton and one electron, and it's the gravitational interaction that causes the proton and the electron to repel each other and thus be separate. And the electrostatic interaction causes the two to attract, and this keeps the electron trapped in a region surrounding the proton. But if the gravitational repelling force that these two particles experience as a result of the gravitational interaction drops, then the electrostatic interaction will take over. It will overwhelm the gravitational force, and the two particles will be drawn to each other, and the atom will basically collapse, and what we will get instead is a neutron, which is a neutral particle. Now, because of the strong attraction between protons, fusion will occur, and will tend to that will tend to the formation of heavier nuclei. And heavier nuclei just have more than one proton in the nucleus, and they can have over 100 protons in the nucleus. And in fact, all the atoms that can form are, well, we know there are so many because we have the periodic table. And so all of these nuclei that we see in the periodic table will be able to form due to the interaction between protons. And so here we see the lithium atom, which is made up of 3 protons and 3 electrons. And these electrons are kept in this region where the electrostatic attraction that the electron senses towards the proton is balanced by the gravitational repulsion that it feels from this proton. And where these two forces are in balance, then the electron will remain trapped in that region. And this is what gives rise to protons. And also because the proton-proton attraction is so strong, it means that the protons will form very close bonds. They will be very close to each other. And then the proton-electron interaction, which is not as strong, will lead to the electrons to be outside this inner layer of protons. Now, the same thing will happen in stars, except instead of protons, we have positive ions that are deficient in electrons. And the densest in protons, ions, will be at the center of the star. So the center of the star will be denser in protons than outer layers. And so we would have ions at the center of the star, and these are atoms that are deficient in electrons. The electrons are separated from the rest of the atom due to the charge separation interaction, or the repelling force between electrons and protons due to the gravitational interaction. And this causes electrons to leave the atoms at the center of the star and move outwards towards the edge, and thus form a layer of electrons where they are basically trapped in the same way as electrons are trapped outside the nucleus of an atom. And now the way an ion forms is an electron absorbs energy in the form of a photon. This is gravitational potential energy, and this causes the electron's repulsion to this proton to increase. When its energy increases because it absorbs a photon, the strength of the interaction, that is the gravitational interaction, increases. So this means this electron will be repelled by this proton. It will therefore be able to move outward. Sometimes it moves to an orbit which is just further away from the nucleus. At other times it leaves the nucleus entirely. So this then we would have 2 electrons left in this atom, and so the atom would be deficient in 1 electron. And that means that it would have 1 extra positive charge due to the extra positive charge that is not balanced by the 2 electrons. And then we would write down, well, the symbol for lithium is just Li, and then we'd add to that the little plus to mean that it has 1 additional positive charge, and this is then a lithium ion. Now, as stars lose gravitational potential energy, the repulsion between protons and electrons decreases, so that these would start combining in the star's outer layers, creating neutral atoms first, and eventually allowing protons and electrons to combine into neutrons. This would result in the star's outer layer being mostly made of neutrons. Thus, a very old star would be likely to have an outer layer of neutrons instead of negative electrons, and thus be a neutron star on the outside, whilst its core would remain positive. Now, what we see here is illustrated is how stars evolve into stellar cores, and what happens as described is that this electric potential difference, which is caused by the fact that there are dense in proton ions at the center of the star, and a layer of electrons on the outside, which are negatively charged, so there will be a negative potential associated with it. So there is an electric potential difference as a result, and this is what drives the light emission of a star. And as the star ages, then this potential difference would decrease, and so the light emission of the star mechanism would be affected. So eventually the star, as it ages, would lose the ability to emit light. It would also grow in size because the attraction between protons in the core, well, actually in the whole star, would decrease, and thus they would move further apart, and thus the star would expand or grow in size. And in the same way, and for the same reason, the star would not be able to attract objects outside it as strongly as before, so this would cause its effective mass to decrease. Eventually, and because stars over time lose electrons, eventually the star would start combining whatever electrons it has left into the ions on the surface of the star, so we would get neutral atoms, and thus a neutral layer, which here is the green, would form on the outside of the star. And as the gravitational energy drops even further, then even the neutral atoms would start collapsing into neutrons, so the star would be left with a neutron layer on the outside instead of a negative electron layer. But it would still have ions on the inside, it would still be positively charged. So a stellar core then would be even larger than an aging star, so it would be much larger than it was as a main sequence star. It would lose its negative layer, the star becomes a positive superion, develops a neutron outer layer, and its effective mass would decrease further. So this old star or stellar core, when it approached the sun, would enter into the sun's corona, and its outer negative layer, and absorb as many electrons as its positive interior would require to be in balance. It would most likely draw a huge current of electrons, which would restore electrostatic balance to the star. It would possibly also cause the sun's driving electric potential to drop, so that the sun stops emitting light for a period of time, thus explaining what happens during the STO eclipse season when the sun actually goes dark. Now, once the star has gathered a layer of electrons to balance its positive status, it will start drawing protons due to the proton-proton attraction that its matter will exert on the sun, and will draw a current of matter from as far down into the sun as its gravitational attraction can reach. The outer neutron layer starts absorbing photons and thus gravitational potential energy, which causes the neutrons to break up into protons and electrons again. This causes this layer to break up. And then through the developing holes, proton-proton attraction causes currents of protons from the sun to be drawn toward the stellar core. And this current of protons will cause a layer of gravitationally energized ions to form close to the point where the star's proton attraction is strongest. And this layer would then spread from there. There would be a layer of electrons also accumulating above this, and thus the star starts to gain an electric potential difference and is eventually able to emit light. Eventually, the star's gravitational potential increases to the point that the gravitational repulsion between the sun's corona and its developing positive layer becomes too large, and the star is ejected. But it will continue to be attracted to the sun, and as it gains more proton matter from the sun, its gravitational attraction to the sun will increase, and it will be able to draw a current of protons from deep within the sun, and possibly reaching down to the bottom of the chromosphere and the photosphere. So this is illustrated here. We see a stellar core with a neutral outer layer, or maybe a neutron layer, being attracted to the sun's corona because it's a super ion, is positively charged. And then once it has interacted electrostatically with the sun and gained a thin layer of electrons to go along with its positive charge, then it will start drawing protons or matter from within the sun, and this matter will form a layer above the core of the object, and this neutral layer will start breaking up and it will be shed, and as the star gains protons, eventually gravitational repulsion between these protons and the sun's layer of electrons will cause the star to be ejected, and but it will eventually come back and draw some more protons and electrons. In the meantime, it can use whatever energy it has gained to emit light, if that's possible. It may also impart some of that energy to other stellar cores. So in conclusion, a stellar core is like a super ion attracted to the sun's electrons due to the electrostatic interaction. Once it draws enough electrons, it will start drawing a proton current and start shedding its outer neutral layers. Gravitational attraction between protons causes it to attract a current of protons, which also anchors it to the sun and allows it to hover in the sun's corona. In the meantime, the sun will be losing gravitational potential energy, protons and electrons. The sun's outer electron layer or corona will thus decrease in size, and due to the huge losses in particle density, huge coronal holes will appear. The sun's decrease in gravitational energy would also manifest as loss in electric potential difference, which will cause the sun to become increasingly darker. And these are the references. This is Dr. Claudia Albers, Planet X physicist. Thank you for watching.